This is a graph of the first derivative, not the f of x function. So it's important to remember that the y values you're seeing are slopes. These are positive slopes. Even if it's going down here, these are still positive slopes. The y values are positive. So that means the original function at this place is going up because the slopes are positive. Going up, going up, going up, going up, going up, going up, going up. The original function is going up in all these locations. And likewise, the original function is going down everywhere where y is negative for the graph of the derivative. So where is the function increasing? It's increasing wherever that the red graph is positive. It ends at 12, so that's why I stopped at 12 there. And then where is it decreasing? It's decreasing wherever that graph is negative. So it starts at 3, because the interval is 3 to 12 for this graph. And 4 is where we stop having negative values. And between 9 and 11, we also have negative values. So the original function is decreasing between those places. Part B says to find a local maximum. And then the next part is to find the local minimums. Local maximums happen when you switch from positive slopes to negative slopes when reading it left to right. Okay? Read this left to right. If you switch from positive to negative, you hit a local maximum. I switch from negative slopes to positive slopes. That's the opposite. That's a local minimum, not a local maximum. I need to switch from positive slopes. These are positive, 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 positive. Switch from positive to negative slopes. So that's a switch from positive to negative. That's a local maximum. And then 11 is also a local maximum. The rationale there is that these slopes are positive. That means your f of x, the actual function, is going up. It might start to level off. It still is going up. And at x equals 9, it stops going up. It's reached its peak. And then to the right of x equals 9, the slopes are negative, which means it's finally starting to go down. So it's hit a local maximum there. And same thing for local minimum, except it's reverse, right? When you switch from negative slopes to positive slopes when reading it left to right, you've hit a local minimum. So 4, negative to positive. Oh, whoa, I messed up here. 11 is not a local maximum. It's got 11 is a local minimum. Because remember, local maximums are switching from positive to negative. 11, you switch from a negative to a positive. Sorry about that. I hope that didn't cause any confusion. Okay, so that's local max, local mins. Local minimums happen when you switch from negative to positive when reading it left to right. Okay, C, find the interval at which the function is concave up. Concavity is a derivative of the derivatives, right? Being concave up or concave down is talking about the derivative of the derivatives. So it'd be nice to have an idea of what the second derivative looks like, and we can make a sketch of that. Think about what all the slopes are. This is a positive slope of the first derivative, so concavity should be positive. Just make a random guess. Doesn't have to be perfect for this. It's a positive slope for the first derivative, so the second derivative is positive. And then the slopes finally level off and become 0 here at x equals 5, right? The slopes are getting smaller. These are still positive slopes. They're just smaller, so we should be getting smaller, getting smaller, getting smaller. And then at x equals 5, we hit a 0 for a slope, and then we continue our decrease. The slopes keep going down until we hit x equals 6. Slopes are negative between 5 and 6, right? This is a negative slope. That's going down when we read it left to right. So between 5 and 6, we should have a negative on our second derivative graph. And then between 6, here, 6 starts being positive to the right, positive, 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 positive. And then we level off and we hit a 0 slope again at x equals 8. So we're positive, and then we come back down, and then we have a slope of 0 at x equals 8. And then we have negative slopes until we hit x equals 10. So negative slopes, but then it comes back up to 0 at x equals 10. That's a slope of 0 right there. And then we have positive, positive, positive slopes throughout for the rest of the problem. Okay, so now we have a graph of the second derivative. Now we can talk about concavity. It's concave up wherever the second derivative is positive. So from the start of this function at x equals 3 to x equals 5, we have a positive second derivative. And then from 6 to 8, we're above the x-axis. We have positive y values, so it's concave up. And then from 10 to the end of the function, we're concave up, okay, because the function ends at 12. Where we concave down, that's where we're negative, where the second derivative is negative. Second derivative is negative between those two. Inflection points are where we change concavity, whether changing from positive to negative or negative to positive. So look, we had positive values for positive values for the second derivative and then negative values. So at x equals 5, we've switched from positive to negative. At x equals 6, we switch from negative to positive. 8 and 10, all four of those are inflection points because they switch concavity from being concave up to concave down.